So our objectives, introduction to digital system, basic logic gates. We'll talk about decimal number system, binary number system, how to convert from binary to decimal and the decimal to binary. We'll talk about octal numbers, hexadecimal numbers, ones complement and the twos complement of binary numbers, signed numbers, binary coded decimal, BCD, and the digital codes. Today we'll cover a part of this, and then we'll continue for the other, for the rest of these items. So what is the signal? What is the signal? The signal is nothing more than a quantity. It changes over time, like this one here. Amplitude, quantity, it changes against time. It can be a constant value or different values, but it is a function of time. Most of our physical world phenomena, such as light, temperature, wind, pressure, speed, are signals actually, but in different forms. So all or most of the physical phenomena we have in nature are actually signals, but in different form, like the voice, for example, is a signal. But this voice cannot be applied directly as input to a system. We have to convert it first. So that's why we use the mic. Mic converts the voice to electrical signal. And this electrical signal applied to the input of the device. Because our system does not understand the input if it is not a signal, either if analog signal, so it is analog input. If it is a digital system, it must be digital. So all physical phenomena are actually signals. Electronic devices cannot directly use a physical phenomena as inputs, as we mentioned. We have to convert it to either analog signal or digital signal. If we have our system is analog, so the signal, the input must be analog. If we have analog and the input is digital, it's like a trash for the system. The same for digital system. If it is digital, the input signal must be digital. Otherwise, it's like input noise. No, it must be the same format of the system. So what is the difference? What is the difference between analog signal and the digital signal? Analog signal is actually continuous signal. The analog signal is a continuous. Okay. Okay. So So, for example, if you look at here, at any instant of time, you have a value for the signal. You have a value for the signal. At any instant of time, you have a value for the signal. So this is what is meant by continuous. And the good example for that, or the most popular example, is the sine wave. Sine, the signal as a sine wave. Of course, most of you study the oscillators. So the oscillator, what is the output of the oscillator? Is sine wave. So sine wave is a good example for continuous signal, analog signal. Digital signal is discrete signal. Is discrete signal. In very general case, something like this. Discrete, not continuous. And the most popular example for digital signal, the bits we see here, logic low, logic high. So this is good example for, or more popular example for digital. So if we have analog system here, if we have analog system, so the input must be analog. The input must be analog, and of course the output is analog. So this most likely work as amplifier. In this case, work as amplifier. So you see the input here, and you see the output. So you can see the amplitude, the difference in the amplitude. In digital systems, the input must be digital, like you see here, and also the output is digital. But of course, different processing based on the function of the system here. So we get digital output with different characteristics. So the transistor we use, the component, the electronic component we use in analog, the main component in analog or digital is the same, is the transistor, okay? Sorry, let me just, yeah. You know the symbol of the transistor, right? So this is the base, this is the collector, this is the emitter. The same transistor. But in analog, analog, it works as amplifier. This transistor works as amplifier. In digital, work as a switch. The same transistor used. This is bipolar junction transistor. So the same transistor used in analog, the same transistor used in digital, but the function is different. In analog, just amplifier. Put small input here, you get at the output here, you get bigger signal. In digital, it works as a switch, on off, as just a switch, on or off. So based on what? How this work in analog as amplifier, how it works in digital as a switch. It depends on the biasing system of the transistor. on the binary system. Like you put here in digital, you put here VCC, and you put certain input here, represent logic high. So based on the biasing system for the transistor, according to the design of the system, so this transistor work as amplifier in analog or as a switch in digital. Examples of digital signals like data transfer. We have either serial data transfer, like between computers, or between computer and the modem. Serial data transfer. We have serial data transfer and we have parallel data transfer. Do you see the cursor or not? You see it?
Yes.
Okay, good.
Yeah.
So this data, either we have serial data or parallel data. So serial data, like between the computer and the modem. This is a good example for this kind of data transfer. Your computer is connected to a modem. Modem stands for modulator / demodulator. So the output of the computer is bits in series. But the transmission line which connect you to the base station or to the internet does not understand bits, understand analog signal, electromagnetic signal. So this modem convert from digital to analog to be transferred by the digital subscriber line. DSL stands for digital subscriber line. This is the line we use for connection between the computer and the base station. And vice versa. The signal or the message coming through DSL is analog. The computer does not understand analog. It must be converted to bits. So now the modem, the second part of the modem, which is demodulator, demodulates the signal and convert it to bits. So the computer can understand. So this is called serial transfer or serial data transfer. And this kind of transfer, of data transfer, we use only one line here. One line we use here. We use one line. So this is good, because if we have more than one line, maybe we have coupling between the lines. So generally speaking, if we have two lines, and say we have current pass here and the current pass here. So when the current pass through a line, it's wire or conductor, so we have magnetic flux created here around the line. Magnetic flux. And the same for the other line also. And so on. So these lines intersect each other. So coupling happens. These lines carry information, by the way. These lines carry this magnetic flux here or magnetic field, carry information. So this very much you feel it like when you use a wired telephone, the old ones, wired. So sometimes you try to call your friend and you hear people talking on the line. You can hear a conversation between persons on your line. And this conversation may be strong or low. I mean the voice. Based on the coupling, if we have more lines intersect each other, so this is strong coupling, or if you have lower voice, so means lower number of lines intersect. So this coupling occurs, which we call it crosstalk. Crosstalk. So you can hear the people because the two lines are close to each other. So coupling happens because there is electricity. The signal path through the line is electricity, like a current here. So you can hear other people's talk. So when we have one line here, in this case, this is good because this means there is no coupling with other lines. So there is no interference or crosstalk. But as you see here, we transmit bit by bit. So this means it's slow. This is slow. So the good advantage here is no crosstalk, but the disadvantage is slow. The other data transfer is parallel data transfer. And as we see here, the bits are transmitted in parallel. This like between the computer and the printer. The data goes from the computer to the printer. It goes in parallel data transfer. So all the signal or the message transmitted at the same time, like you see here. So we use more lines here because each line carry a bit. The duration of the bit is called clock tick. So in one clock tick here, we can send all the bits. But you can see here, how many clock ticks here we need to transmit this signal here. Can you tell me, please? You can type it. You can type. So I can see your name and give you a bonus credit. How many clock ticks here in this serial transfer based on the data we have here? Okay, good. So I have many people actually answered. So just hold on. Okay. Uh, okay, 15. Okay, thank you. Wilton. Okay, thank you. And okay. Yeah, 11 clock tick here. So this one clock tick, 2, 3, 4, 5, 7, 6, 8, 7, 8, 9, 11. It's 11. 11. If you count these bits, it is 11. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So that's why it is slow. We send the message here in 11 clock ticks. But here we send the whole message in one clock tick. So this is good. It's faster. But unfortunately, what happens here? What happens here? We use more than one line. So this means we have crosstalk here. Okay. But of course, we need this and we need this. Okay. We need both. But we have advantages and disadvantages. Okay. Any question so far, please? Any question? Please, if you have any question, ask me. I will look at the problem for the voice, and hopefully next time it will be fine. Okay. Any question, please? 6, 8, 6. Okay. Okay. Steven Price. Okay. I see. Try is okay. Um, bank, bank, bank is okay. Yeah, sure. Fatima, Fatima, okay. Shin, okay, okay. Okay, great. So, of course, most of equipments now are converted from analog to digital. Uh, so why we look at digital systems? There are many advantages actually. Among them is more easier in design digital system more easier than analog. Because you know in the design here you deal with low level of voltages. So like around 5 to 18, this is VCC, or the voltage to bias the transistor based on the type of the IC is between 5 to around 18 volt. And when we look at the data sheet for any IC, the biasing or the voltage for VCC is between 5 to 18 volt. So this low value of voltage used in the design make it easier than, of course, higher voltages. And consequently, the weight is light. Or most of the digital equipments, you can see the light is weight. I mean, the weight is light. The smaller size also, accuracy is higher, and storage is easy. So this like examples for why it is better than analog. But disadvantages like the bandwidth is limited, the high speed analog to digital ADC analog to digital converter or digital to analog converter are expensive. So this like is the main disadvantage. In digital, in analog, before we go to digital, in analog system, we use our regular numbers, which 10 symbols from 0 to 9. 0, 1, 2, 3, 4. Any number we use it is within these numbers from 0 to 9. But in digital, we use just two numbers, which you call binary digits, is 1 or 0. We use either 1 or or 0. 1 or 0, so it's called this bits. So the digit, it can be from 0 to 9, 0, 1, 2, 3. But binary digit is either 0 or 1. So bits actually came from binary digits. So we take the first letter here and the last two letters. So bits. So 1 and 0 is actually inside the circuit are voltage levels. Are voltage levels. In the circuit does not understand anything, either we have voltage drop or current pass. So yeah, we express this in presentation like bit 1, bit 0, but this bit 1 or bit 0 is actually voltage value for voltage inside the circuit. So 1 is called also logic high. Logic high. And this logic high, as I mentioned, is like between 5 to 18 volt, most likely. So most likely between 5 volt up to 18 volt. So this is called the logic high. 0 is called the logic low. And this also another level of voltage. So it can be 0 or like 0.3 volt, 0.2 volt, something like this. It depends on the design, as I mentioned. So 1 or 0, bit 1 or bit 0 actually represent logic high or logic low, and these are voltage levels. So two different voltage levels are used to represent the two bits 1 and 0. Most likely bit 1 is represented by the higher voltage, or we say high. And the bit 0 is represented by lower voltage or low. So 1 equivalent to logic high, 0 equivalent to logic low. So if we look at this simple figure here, so logic low is actually is a range. Like I mentioned, it goes for logic low, it goes from 0 to like 0.2 or 0.3. Logic high, it may go from 5 to 18. So we have ranges. So low, like between VL minimum, V low minimum, and VL maximum. High, between V high minimum and V high maximum. And there is a gap between the two levels, level low and the level high. There is a gap. And this gap actually is like to avoid overlapping between logic low and the logic high. But it should be like quick transition from low to high, because the status we have for the system, either we have logic low or logic high. So this is just a gap to avoid overlapping, but the operating point of the transistor passes this very fast between low and high. If you, I'm not sure you studied this or not. For the curves of the transistors, okay. So you have these curves of the transistor. Any transistors like the one we drew before, And we have a load line here. And this is called the Q, the operating point. So here we have a region. It's called the cutoff region. Cutoff region. And we have here a region called saturation region. Saturation region. So if you follow with me, you can I read what I write. So just to follow me. So this region here is active region. Where if the operating point of the transistor lies here in this region, so this work as amplifier or analog. If the operating point jump between here and here, so jump between the cutoff and the saturation. So for here and here, the transistor work as a switch, as we mentioned, on, off, on or off. So on in the saturation, this Q point jump here. Off, the Q point jump here. But in analog system, the operating point of the transistor lies here in this active region. It's called the active, it's called cutoff region, it's called saturation region. So that's why, this is the difference between the transistor, how it works in analog system and how it works in digital system. It's actually based on the biasing, as I mentioned. This Q either lies here in the active region for analog, or the biasing of the transistor enforces the transistor to work between this point here and this point here, either in the cutoff for the transistor to be off, so non-conduct, or the transistor to be on, so conduct. Okay, so this is just a reminder for how it works in active region or cutoff region or saturation region. The types of circuit implementation or technology used, as we mentioned before, TTL technology using bipolar transistor like this one here. This is the symbol for bipolar transistor. And you will see in the data sheet, this TTL technology, the IC always start with 74. In the data sheet or even in the IC itself, you will see this IC start with 74. So this means the technology used here is TTL. And the type of transistor we use is this transistor here, which is called the bipolar junction transistor. CMOS is another technology, complementary metal oxide semiconductor, and the transistor used here is called MOSFET. MOSFET, and the symbol for this transistor is this one here. It's different technologies, different manufacturing. So here in the TTL, we know this is the base, this is the collector, this is the emitter. But in CMOS, this is the base is called the gate, G. The C is called the drain, and the emitter here is called source here. And the number in this IC start with C. C letter. in CMOS, but in TTL start with 74, most likely. Okay. Digital waveforms. This is called the digital waveform. Any signal, you can call it waveform. Simple. Okay. So this is periodic digital waveform. Periodic means we have periodic or non-periodic. Periodic means the pattern of the signal repeat itself. Each big T, big T. What is big T? Big T is called the period, which is the time interval between any two similar points. Like this point here and this point are similar points. This point here and this point are similar points. This point here and this point here are similar points. How I know? Just look at the behavior of the waveform before and after this point. So before like this, after like this, which has the same features here. So these 2 points are similar points. So the time interval between these 2 points is big T, the period. Or this point and this point. Look at before and after. Before and after. So between here and here, this also big T. So if the pattern of the waveform repeat itself after big T, it's called periodic. So like when we reach here, the pattern start to repeat itself. Or when we reach here, the pattern start to repeat itself. If it is non-periodic, this not happen. It doesn't repeat itself. You see different things. Okay. So please, what is your name? What is your name? The iPhone guest. What's your name?
Arthur.
Can you type it, please? Because I don't hear you well. Can you type it? Chat with me, please. What's your name? Arthur? Arthur. Okay, thank you. Okay, got you. Okay, guys. So periodic means the pattern repeat itself each big T. A big T is important parameter in the waveform because from this big T we can get the frequency of operation of the system. So we can see frequency F equal 1 over big T. It's better when you calculate anything or use equations to use standard units, especially if the equation is complicated, like there are many parameters in the equation. So to avoid any errors, use the standard units, like what? Frequency in hertz, this is a standard unit. T as time is seconds. For example, data rate, bit per second. And so on. A distance in meter, or lambda, or the wavelength in meter. So use standard units. So when you substitute about the values, say for example, here is this equation. When I substitute for t in seconds, I get the result I get in hertz. Then the final result you can convert it to like a kilohertz or megahertz, whatever you want. This may be easy if we have simple equation. You can use other units, but it's better to avoid any errors. Use the standard units and then convert. Like for example, when we calculate this, we got 1000 hertz. As engineers, we can't leave this result like this, 1000 hertz. So we have to say this equal to 1 kilohertz, for example. Okay? Because at the end, you will most likely write the technical reports and the research. So of course, you present your work in the best of all. So you can't present your work with calculations like frequency equal 1000 hertz, for example. You have to put it in 1 kilohertz and something like this. Or 10 to the power 6 hertz. You have to put megahertz. Duty cycle, so the frequency is 1 over big T. And also big T is 1 over F. It's the same. Duty cycle is defined as, you see this time interval where the bit in logic high, and this time interval which the bit at logic low or 0, and the total from here to here, as we mentioned, is big T. So the duty cycle is T high divided big T. Big T is T high plus TL. T high plus T low. This gives us the total period. So the duty cycle is T high divided by big T. It is a ratio because you divide the time by time. So second cancel with second. So this is a ratio. There is no unit for this. But most likely we need the duty cycle as percentage. Any ratio to convert it to percentage is simply just multiply by 100 and divide by 100. So we didn't change the formula. We just try to put it in another form. You can change the formula from one form to another. So whatever you do, add, subtract, divide, but you must do the same thing. I mean, you is not allowed to change the formula. So here we multiplied by 100 and divide by 100. So we didn't change anything. Still, if we cancel this out, still the original ratio is there. But we do that to convert it to percentage. So this 100 here inside a box, don't touch. Just multiply the ratio by 100, and this 100 in the box will be converted to the percentage. So say this ratio is 0.3. So 0.3 multiplied by 100, what we get? Perfect. Thank you. Really? Riley? Okay, thank you. Thanks. 30%. 30%. So now we convert from ratio to percentage. Okay, is this clear for everyone?
Yeah.
Okay, this is a good question. This is actually my next question. One of your friends asked about why, I mean, what is the benefit of of this duty cycle? Can anyone answer this question? Can anyone tell me why this is important parameter to get? If you look at any catalog, you will see like the frequency, duty cycle. So what is the benefit of this? Yeah. Okay, perfect. Chen, good. Thank you. Chen, what is your code number, Chen? What's your code number? Oh, okay. Perfect. Yes. 7. Thank you. Yeah, exactly. Duty cycle indicates, is this something related to the life cycle of the equipment? So when you say it's 50%, for example, what this means? If the duty cycle is 50%, what this means? This means T high is okay. Okay, thank you. T high is equal to T low. T high means when the system is on or the transistor is on. If the transistor is on, so the system is on, all right? So this means the time of operation or the time where the equipment is on is half the whole time of operation. Like say the equipment is used for 1 hour. So half hour the transistors are on and half hour the transistors are off. So this is the meaning of a duty cycle. So it indicates how much time the equipment is on relative to the total time you use the equipment. Now we'll talk about the basic logic operations, basic ones, and then next classes we'll talk about the rest of all gates we use because we need all of them. The first one is called not operation or inverter. Not operation or inverter. And the symbol of this not operation or inverter is like this. Please remember here we have a bubble here. We have a bubble here, okay? So it's simply one input and one output. So if the input is A, in general, A can be bit 1 or 0. The output is A inverted. You see this bar here? This bar either written like this or can be written like this. Because you don't have this on your keyboard. So you can use this symbol as A inverted if you type it. A inverted means if A is 1, the output is 0. The invert of 1 is 0. If the input is 0, the output will be 1. Yeah. So this is the function of this inverter. So if we draw the truth table, each digital equipment or component, it has truth table. Truth table gives us the relationship between the inputs and the output. Like if we have these inputs, so the output must be like this. And this is the function of the system. So it's simply how many different combinations we have here? We use 1 bit. The input is 1 bit. But we use either 2 or 1, 0 or 1. So it's 2 to the power 1 equal 2. So for this case here, we have only 2 different combinations, either 0 or 1 as the input. So in this case, the output, if the input is 0, the output is 1. If the input is 1, the output is 0. So this is a function of the inverter. Okay. The second basic gate is AND gate, and operation. So we use AND gate, and operation related to the AND gate. Except the inverter, and only the inverter have only one input. The inverter has only one input. But all other gates, it can be 2 or more inputs. But still we have one out. But the inputs, other than the inverter, it can be 2 or more. Most likely 2. But if it is expandable gate, so the inputs can be more than 2. Okay? So, AND operation, okay, before we go to AND operation, let me talk little more about this inverter. This inverter actually, as we mentioned, this is just a symbol. But inside this symbol, there is a circuit. So one may say, oh, how if we put 1 at the input or logic high, how we get 0 at the output? If we look at the circuit, simply, so simplified circuit just to get the idea how this works. So we have here, this is the emitter connected to the ground. The ground means 0 volt. And this is the base, and this is the collector. Here's the collector, okay? We mentioned the collector, we have here like 5 volt, or up to 15, 18 sometimes, based on the IC. So 5, which represent high, logic high. 5 represent logic high. 0 represent logic low. And we mentioned this transistor work as a switch in digital. So this transistor must be work as a switch. And we take the output from here. And the input is applied here. So based on this biasing system, if we apply 5 volts here, which is logic high, at the input, which is here, we apply here at the input, 5 volt. So what happens here? You see the voltage drop here is higher than the voltage drop here. On the base, the voltage is higher than the voltage in the emitter. This is the emitter. If this is the case, so this transistor is on. So the transistor is on. Or conduct. Conduct means what? Means this point is connected to this point. Because we mentioned this is nothing more than switch now. So if it is on or conduct, this point is connected to this point. So what is the voltage here at Y? What is the voltage? This Y connected directly to the ground, which is 0 or low. So we have low, 0 volt or low. So you see here high goes to low, or 1 goes to 0. Okay, now if we have If we have 0 here, if we apply 0 volt at the base, 0 volt means low, logic low. Now what we have? We have 0 voltage on the base, we have 0 voltage on the emitter. So if the voltage on the base equal to the voltage on the emitter or less than, so this will be non-conductor. The transistor non-off is off or non-conductor or off. What is meant by off? Means this point not connected to this point. So this output goes directly take the voltage from here. So now this gives us high here for this case. So we have 0 here, we have 5 here, or we have 0, bit 0, we have bit 1 here. So this is very simplified circuit to just show you what happens inside this symbol. Okay. So this is how we got the input inverted as the output for this not operation or inverter. Now for AND gate, any question here, please? Yeah, as we mentioned here, if the input is 1, the output is 0. So if the input at the base of the transistor is logic high, the output at the collector will be logic low. Okay? For AND operation and vice versa, of course, if 0, so we get 1. So in AND operation, we have two inputs. We have two inputs, A and B. And for AND operation, okay, because because the communication is hard now, little hard, so we may talk more in more details next time. Okay, it will be easy. But let me finish this before we leave, please. So for the AND operation here, the AND operation is actually logic multiplication. And means logic multiplication. Logic multiplication, okay? We'll talk, okay? So if the input A and B, the output is AB, logic multiplication. And how many inputs here? How many inputs we have here? 2, all right? So 2 to the power 2 equal 4. So we have different combinations, different states. So for the inputs. So if A and B, so it can be 0, 0, or 1, 0, or 0, 1, or 1, 1. And the simplest way to write these different combinations, just about 0, 1, 0, 1, and then double the numbers. So 0 is 0, 0, then 1, 1, 1. If we have more, double the numbers. So it will be 0, 0, 0, 0, 1, 1, 1, 1, and so on. Okay? We'll do a lot of this in the next class. So we have 4 different combinations. And based on the operation of this AND gate, which is logic multiplication, so we just multiply the 2 inputs. So 0, 0 gives a 0 output, 1, 0, 0, 0, 1 is 0, 1, 1 is 1. 1, 1 is 1. So please, here I need every one of you. Tell me what you see here. What is the remarkable thing here you can see in this truth table? Okay, just type, please. Just type. What you notice here is remarkable. what you notice here in this truth table. Yeah, we mentioned the functions multiplication, logic multiplication, but what you see here? No, no, not addition. And operation is means multiplication, logic multiplication. Perfect. James, okay, hold on. James, thank you. James, perfect, James, thank you. Exactly. James mentioned here. Look at here. The output 1, you see all outputs are zeros, except this case here. The output is 1 here if and only if the two inputs are ones. If and only if the two inputs are ones. Okay. Okay, thank you. Chin also mentioned, and Dash. Okay, thank you. Thank you. And this is very, I mean, a very important point. When we have, like, if someone asked us if we have bit streams, inputs, bit stream, not only one bit here and for A and B. No, if we have bit streams and we need to get the output waveform, uh, of course, it's not reliable to go through bit by bit. Here we have 1, 1, so it is 1. 0, 1 is 0. This is not reliable at all. If we have, especially if we have long bit stream. So what we do? We look at the bit stream, the two inputs, and we just, for the output, to draw the output, we look at where the ones, where both inputs simultaneously are ones. As these two inputs here, both of them are ones, the output will be 1. Other than this, the output will be 0. Whatever A is 1 and B is 0, or A is 0 and B is 1, whatever. The output is 1 only if the two inputs simultaneously are ones. So we look at the input A, input B, and we draw the transitions for the bits. And when we have two bits, A and B, both of them are ones, so the output will be 1 in this time duration. And then 0 until we see the two inputs are ones, so we have 1. Okay? Everyone see what I'm saying? Please say yes, or if you have any question, ask me, please. Okay, good. If you don't have questions, this means it is okay. That's what I might understand. Okay, so please tell me if you have any question. Now the other one is OR operation, and OR operation, the symbol like this, the and gate, or AND operation, the symbol like this, and I put sign of multiplication here just to remember this is logic multiplication. For OR operation, you see I put plus here because OR operation actually is logic addition. Logic addition means what? Means 0 plus 0 is 0. If the two inputs, 0 and 0, so 0 plus 0 is 0. 0 plus 1 is 1. 1 plus 0 is 1. 1 plus 1 is 1. Remember, this is logic addition. So 1 plus 1 is 1. This is different than binary addition. In the gate, in the OR gate, we deal with logic addition. But binary addition is different. When we add 1 plus 1 in binary addition, is what? In binary addition, In logic addition, exactly. Thank you, Josh. Oh, okay. Thank you. Hold on a second, please. Hold on a second. Uh, just 1 second, please. Okay. Thank you, Bang. Bang. Okay. And the Castro also. It's good. Castro. 0, 1. 0 is carry 1. 0 is carry 1. When we add logic addition, we say 1 plus 1 is 1. But binary addition, one plus one is 0 with carry 1. Carry 1. And is written as like this. 0 is carry 1. Why? Binary addition, like 1 plus 1. In our regular math, 1 plus 1 is equal to what? 2, right? So in binary addition, you can't say 1 plus 1 is 1. Is 0, 1. 0, 1 in binary. How we read this 0, 1 in decimal? This is equivalent to 1 and 2. So 0 times 1 is 0 plus, so it is 2. Right? In this as a decimal number. So in binary addition, 1 plus 1 is 2. I mean equivalent to 2. And this is not equivalent to 1. So binary, we'll talk about this conversion in details. So don't worry. I just, because some students confuse, unfortunately, when we talk about logic addition and the binary addition. Logic addition is completely different than binary addition. Logic addition, we add 1 plus 1 is 1 as a function of the gate. But in binary addition, we add the numbers in binary, which exactly equivalent to the decimal. If we add the decimal numbers or our regular numbers as decimal values, as symbols from 0 to 9, is equivalent to if we add these numbers in binary format. It should lead to the same answer. So when we add 1 plus 1 as binary, in binary, is this equivalent to 2? 2 is not 1 in binary. 2 is 0, 1 in binary. So that's why we say 1 plus 1 is 0. It's called 0 with carry 1. This is the exhibition for this. Okay. We'll talk about this in details. Okay. So don't worry. Don't worry now. We'll talk about it in details if it is not clear yet. Decimal numbers system. As I mentioned, the decimal system is the most familiar to us because it is a tool that we use every day, like your banking account, whatever calculations you do, we always use from 0 to 9. Any combination between 0 and 9, which is 10 symbols. So that's why we say decimal number is the number for base 10, because we have 10 symbols from 0 to 9. So the weights of this decimal number, if we have this number, for example, 2045.214. So the weights, the first weight here is 10 to the power 0, then 10 to the power 1, then followed by 10 to the power 2, 10 to the power 3. So what we read here, 2,745. After the decimal point, the first weight here is 10 to the power negative 1, then 10 to the power negative 2, then 4 times 10 to the power negative 3. So this is like a 0.2 or 0.21 or 0.214. Okay. Binary number system, as we mentioned, we use only two symbols. Only two symbols, 0 or 1. So when we put the number as binary number, we put base 2 here. But for decimal, we put base 10. And we'll talk in more details, of course, next time. I post a simple homework based on what we mentioned here. So as I mentioned, homeworks are individual submission. Everyone must submit the homework. And please submit on time to avoid losing any points. Okay. Any questions? Any questions, please? Any questions? Okay, so if we don't have questions, I wish everyone have a good day and see you next Thursday at the same time.
I
Okay.
got one question.
Okay, thank
actually.
you. Bye.
Oh.
Okay, take care, everyone. Bye.
Thank you.
You're welcome. Take care.
Thank you, Professor.
Thank you, sir. Take care. Bye. You too. Take care.